Okay, so we're going to learn about induction. Induction is a really important part of proving stuff, and it's directly related to recursion. Recursion is a very important part of computer science because a lot of the problems that we want to solve can be expressed very elegantly and succinctly recursively. And to prove that they actually solve the problems we say that they're going to prove, we use induction. So there's a relationship between induction and recursion, but they're not the same. When we talk about something that's recursive, we talk about something that's defined by a smaller version of itself. When we talk about induction, we talk about what's called the inductive hypothesis. That is, we're proving something by assuming that it's true in the base case, and then proving that if it's true for the base case, it must be true for every intermediary case. That's what we call the inductive proof. So the easiest way to kind of understand this is with an example. So let's take a look at example 1. So example 1 has what we call an assertion A of n. So this means that this assertion is true for the value n. And our assertion is every n that's greater than or equal to 2 is a product of primes. So every n greater than or equal to 2 is a product of primes. So let's just start listing them off here. 2, well, it's a product of 1 times 2. 1 and 2 are both primes. 3, the product of 1 times 3. They're both primes. 4 is a product of 2 times 2. Primes. 5 is a prime. Anytime it's a prime, you know it's the prime number times 1. 6 is 2 and 3, which are both primes. 7 is a prime. 8 is 2 times 2 times 2, which are primes. This is kind of the intuitive understanding, right? Any number that is the product of other numbers, those numbers can be broken down into their products until eventually all you have are primes, because you can't break down primes any farther. That's why this is true. Every number must be the product of primes. So let's go up much higher. 112. Well, that's going to be 2 times 56, which is going to be 2 times 28, which is 2 times 2 times 14. Oh, there's another 2 in there. Which is 2 times 2 times 2 times 2 times 7. So, I mean, it's intuitive. Any number is the product of primes. Any number greater than or equal to 2. That's our assertion, okay? For us to inductively prove this assertion, we need to establish a base case and establish what's called an inductive hypothesis. So, if we're saying greater than or equal to 2, that means our n sub 0 is 2. That's what we call our base case. Our inductive hypothesis is going to be, suppose that for some n that's greater than 2, a sub k is true for all k such that k is greater than or equal to 2 but less than n. Right? So k is somewhere between 2 and n. That's our hypothesis. We are assuming that to be true. If that is true, then is a sub n true? That's the question. Well, what are the possibilities? One possibility is, I'm going to kind of do our possibilities in a big curly brace. N is prime. Right? If n is prime, then it's true, right? Because n is a product of n times 1. If n is not prime, then n is the product of two numbers s times t. And I don't know what those numbers are, but I do know that they're less than n. Well, guess what? That means that they are covered by our inductive hypothesis, right? Those values k go from 2 all the way to 1 less than n. So S and T both are the product of primes according to our hypothesis. If it's true for both of them, since they're the product of primes, we multiply all those primes together, we get n. N must be the product of primes. That is our proof. Now, what you might be thinking is that sounds kind of like bullshit, right? And it is. It's only true if our hypothesis is true. And aren't we trying to prove that hypothesis? No. With induction, we assume the hypothesis is true for everything less than n and prove it for n, right? This is what's called strong induction. Okay, so the terminology that we need to have in our minds when we're talking about induction. Our assertion for n0 is our base case. That is our simplest case. This is the simplest possible scenario where we can prove it's true in this one case, usually just by plugging in the numbers. Our assertion of k is our inductive hypothesis. So this is what we're assuming to be true. And then our A of n is our inductive step. That's the thing that we actually have to prove. If the base case is true and the hypothesis is true, then we prove that the inductive step must be true. Now, if the inductive hypothesis was not true, then the inductive step becomes not true. However, because of the nature of induction, if the inductive hypothesis wasn't true, we would not be able to prove the inductive step, right? Think about it. If it wasn't true for n sub 1, I couldn't prove it for n sub 2. And if it wasn't true for n sub 2, I couldn't prove it for n sub 3, and on down the list. So that is how induction works. It's a little kind of, to wrap your mind around, but it's true. So that is what this unit is. This unit is really just going through induction, establishing a base case, a hypothesis, and then doing the inductive step. And we will, there's really not a lot in terms of examples. This is a much shorter chapter than anything that we've done before. However, there's more in terms of things that we need to, work that we need to do in order to understand it. Induction is more of a wrap your mind around it kind of thing. Okay? So that is the definition of induction. That is example 1. Oh, one last thing. I mentioned that this is strong induction. And it is strong induction because k can be anywhere between 2 and 1 less than our n. In weak induction, k is n minus 1. That is, we only prove it for the one smaller than our inductive step. For our purposes, it doesn't really matter, but you should know those terms. Strong induction means for any k between our base case and our inductive step, it's true. For weak induction, we're only proving it for one smaller. And as you see from the definition of induction, it doesn't really matter, because even if you're only proving it for the one smaller, you can keep going down the inductive ladder until you get to your base case, and that proves it for all possible cases anyways. Okay, so that is induction. If you have any questions, ask them in the forum below.